Good morning. So today I'm going to discuss some recent results that were obtained by our research group on an unusual crystallization pathway observed during the formation of metallic solid solution. And I'm going to say a few words about the pivotal role that ordered precursors can play in this nucleation pathway. So crystallization is, of course, a very, very important process that's key for many types of applications. That includes the formation of pharmaceuticals, catalyst materials, so it applies to a wide range of materials. And what we know for crystallization is essentially based on classical nucleation theory. So basically, I mean, we have the situation, for instance, we think about a liquid nanoalloy of copper and nickel. So that's the example on the left-hand side. We know that the height of the free energy barrier is, for instance, going to be resulting from a competition between two terms. First, the fact that the liquid is going to transform into the solid phase, the crystalline phase. That's going to be the stable phase. So that's going to be a term that's going to be favorable in terms of free energy. So it's going to be this volume term. And of course, there is going to be the counterpart to that, a term that's going to be unfavorable from a free energy standpoint. And that's going to be the formation of an interface between the liquid and the solid as crystallization proceeds. So what we know from the classical nucleation theory is an estimate for the height of this free energy barrier. And we also know that the further away we get from the crystallization point, the phase transition point, the easier it's going to become to carry out the nucleation and the crystallization process. So that's what we see on the left with the decrease in height of the free energy barrier as the temperature gets lower and lower in the system. And of course, I mean, there is a whole range of issues that are going to be key for the applications that I was mentioning about pharmaceuticals, catalysts, and that issue is the control of the crystalline structure that's obtained as the outcome of the crystallization process. So basically, the issue of the control of polymorphism. So now today we are going to look at the crystallization into, from a liquid nanoalloy, so composed of two types of metallic atoms. And we are going to ask ourselves whether crystallization is always going to occur through an increase in organization within the system. So we know, some empirical rule that's known as the Oswald step rule that was proposed at the end of the 19th century, which states that crystallization is going to occur through a series of stages that are going to result in a gradual onset of order until the stable polymorph has formed. So here we are going to focus on the crystallization of a solid solution, and that's really a problem that's, or a question that's of importance to many, many applications. So for instance, solid solution have been shown to play a major role in applications for water splitting, hydrogen production, and of course, I mean, one of the key aspects is the formation of high entropy alloys. So what we're going to do today is to take a simple test case, which is going to be the crystallization of a copper gold liquid alloy. So we're going to vary the composition. So the X here, the ratio of how much copper there is going to be in the system with respect to gold. And we are going to examine the crystallization process in this system. And the added level of complexity here is going to be the fact that there is going to be, during crystallization, a competition between the formation of the solid solution, so if you will, a chemically disordered structure, closed-packed structure, and the formation of ordered solid phases. And obviously, in that case, there's, in addition to the structural order, there's also going to be chemical order. So the distribution, the relative distribution of copper and gold atoms are going to be done according to the L10 phase or L12 phase, depending on the ratio that we have for copper and gold in the composition of the alloy. And because of this competition, as we will see, there are going to be some arising issues of what is going to be the actual crystallization pathway in such system. And to shed light on the process, we are going to carry out molecular simulation for the crystal nucleation process. So doing these simulations, I mean, we are going to carry out a well-established method that's going to be the umbrella sampling simulation. We are going to use a reaction coordinate, Q6 here, which is going to correlate with the onset of crystalline order with the system. And we are going to examine what's going to be the height of the free energy barrier for each of the compositions that we are going to consider here. So on the left-hand side, so I've summarized results from our simulations, and we are going to have, for 3 different compositions, we are going to see that there is a non-monotonic behavior in terms of the height of the free energy barrier. So specifically here, what we can see on the left is that when the composition is 50-50, so when there's as much gold as there is copper within the system, we are going to obtain a much higher free energy barrier of nucleation than when we have a 1:3 or 3:1 ratio between copper and gold. So that means that we are going to have a composition-dependent free energy barrier that's going to vary non-monotonically over the composition range. So that's definitely something that's unexpected, and we are going to try to shed light on this phenomenon and understand why we are going to have, for instance, such a low barrier for the 3:1 and 1:3 ratio in terms of the composition of gold and copper. So in order to figure out what's happening here, we are going to be able to examine what happens in terms of the composition of the critical nucleus, or what are going to be the properties for the critical nucleus. So for that purpose, we've computed 3 types of analysis for the critical nucleus. So we have the variation on the overall size, so how many atoms are going to belong to this critical nucleus. So that's what I've shown here across the composition range, as with the circles here at the top. And what we can see is that there is a monotonic variation in the size, number of atoms belonging to the critical nucleus across the composition range. So again, I mean, the x-axis, that's the fraction, the mole fraction in copper. So we have a monotonic variation, so that doesn't correlate with the non-monotonic dependence of the height of the free energy barrier upon the composition. When we look at the fraction of Cp-like atoms, so that's the insert here, we are going to see that, again, we see some monotonic variation across the composition range in the fraction of Cp close-packed atoms within the critical nucleus. So again, monotonic variation doesn't correlate with the non-monotonic variation in terms of the height of the free energy barrier. But the one thing that we were able to pinpoint in the analysis of the structure of the critical nucleus was the non-monotonic variation in the percentage, in the fraction of ordered like atoms within the critical nucleus. So that's what we see here. We have, let's say, higher fractions in ordered structure within the critical nucleus. So that would be the L1,2 phase at 25% of copper and 75% of copper, so the 2 extreme points, if you will, out of the 3. And we have a much lower fraction in the ordered phase when we have a 50-50 composition. Okay, so that's the first clue as to why we observe this non-monotonic behavior in the height of the free energy barrier. So now let's examine what happens in terms of the structure of the underlying supercooled liquid. So in that case, I mean, what we can see is obviously we can compute the radial distribution function, so the pair distribution function between copper atoms, and examining what happens across the composition range, we see that, well, you know, we see some kind of regular, well, for instance, behavior, monotonic behavior in terms of the structure. So the reason why we're specifically interested in the structure of the underlying supercooled liquid is, of course, because of, you know, what, for instance, Frank has examined, in the sense that the presence of locally favored structures, for instance, icosahedral defects or icosahedral cluster within the liquid, is going to impact the crystallization process, the formation of well, closed-packed structure. And of course, I mean, when we think icosahedral, we know that this kind of order is going to be incompatible with the onset of a closed-packed structure, with the onset of any crystalline structure. So it makes sense to actually look for these locally favored structures, so structures, if you will, clusters that are going to be of very low formation energy, very low energy, and to see if that could account for any non-monotonic behavior. So we see that it's not, we don't see anything remarkable in the pair correlation function at the top. And now we look at the presence of icosahedral clusters, so how many of them there are in the system, what is going to be their formation energy. And what we can see is that, again, we do not see anything remarkable with the 50-50 composition. So again, I mean, here, for instance, I mean, we see that there is well, close to an overlap in terms of the concentration of the cluster per cubic angstrom. We see that, you know, find roughly the same thing, for instance, whether there is 25% of copper or whether there is 50% of copper. So we don't see anything remarkable in terms of icosahedral order. And that means that the presence of more or less icosahedral order here, the presence of the icosahedral order period is not going to be a factor in the crystallization process here. So we turned to a different type of analysis, and we looked for the presence of ordered cluster within the supercooled liquid. So for that purpose, I mean, we carry out a similar kind of analysis to what we did for icosahedral order, except that we are going to look at the concentration, so that would be the y-axis on the right of the plot, and we also look at the formation of energy of this ordered cluster, that would be on the left. So in terms of formation energy, so that's these are the symbols shown with the circles, we see that we have a non-monotonic behavior across the composition range. So again, something that correlates well with the non-monotonic behavior in the height of free energy across the composition range. Similarly, if we look at the concentration on this ordered cluster within the supercooled liquid, so well before any well before we actually start the nucleation process, we see again that there are many more ordered clusters that are going to appear within the liquid. So that's what we have, this non-monotonic behavior with the triangles this time around, which correlates well with the non-monotonic behavior in terms of formation energy with the circles, and again, which correlate with the non-monotonic behavior that we see for the free energy barrier of nucleation. So again, what we see here is that it's very easy to form L12 clusters, which take place in systems with 25 or 75% of copper in the liquid nanoalloy. On the other hand, it's very difficult from an energy standpoint to form clusters of the L10 phase. So it's very difficult to form such ordered cluster for the 50-50 composition. And as a result of this higher formation energy for these clusters, L10 clusters for the 50-50 alloy, we see that such clusters, and that's what the triangles show, occur much, much less frequently. So that means here that we've been able to correlate the presence of this defect, the fact that they are very easy to form, the fact that they occur much more frequently. We have been able to correlate this non-monotonic behavior to the non-monotonic variation that we see in the height of the free energy barrier. So again, what we've been able to do with this data is to account for the fact that it's going to be much easier to crystallize much lower free energy barrier of nucleation when we are dealing with 25 or 75% in terms of mole fraction for copper in the liquid nanoalloy than it is, for instance, for a 50-50 composition. So essentially, what we can postulate at this time is that these ordered clusters are going to serve as a precursor for the nucleation process. And to really check that, I mean, we analyzed what happens throughout the nucleation process. And that is one example on the left before nucleation is going to actually start. This is an example of the status, if you will, of the liquid nanoalloy. So what we have here, I mean, with the bigger spheres, are going to be here a copper atom at the center, which is going to be shown in, let's say, in tan, circled, or if you will, surrounded by 4 atoms of the other nickel. And that's one of the clusters that has been identified as with the L12 structure. So an ordered cluster here, and we show just a few of the atoms within that cluster for clarity. What we have around, I mean, and the yellow spheres that are going to be shown here on the left are going to be the icosahedral defects. So of course, I mean, there are icosahedral defects. I mean, and that's the copper atoms that are going to be identified as being with a, let's say, icosahedral environment. So of course, there are all these icosahedral defects, but as we've seen, they do not play a role in the nucleation process, and they do not impact, I mean, the change in height of the free energy barrier. And of course, I mean, the liquid atoms, liquid-like atoms are going to be shown here as translucent atoms. So we have these clusters that form, and these clusters are going to be at the beginning of the nucleation process. And that's something that we see, and they're going to remain on the surface of the crystal nucleus as the nucleation process advances. And typically, that's what we see on the right-hand side. So that's what we get at the end of the nucleation process. So when we have a critical nucleus, and what we can see here is that there are, for instance, here on this snapshot, there are a couple of ordered clusters that form on the surface. So what happens is that the formation of these ordered clusters of very low energy, this locally favored structure is going to promote, it's going to serve as an anchor, as a way to promote the onset of crystallization. And throughout the nucleation process, these ordered clusters are going to keep forming on the surface of the nucleus, and they're going to keep promoting the nucleation process, hence the lower free energy barrier of nucleation. So what we've been able to see today is an unexpected nucleation pathway that's going to involve a more ordered intermediate than the actual final crystallization product. So that's fairly unusual in the sense that we expect that we start from the liquid, which is completely disordered, both from let's say, a structural standpoint, and both from a chemical, or if you will, compositional standpoint. And what we would expect is that we get towards the crystal, and of course, all these steps that Oswald thinks about, and well, foresaw were crucial in the onset of order and in the crystallization process. We see that in fact crystallization doesn't occur, if you will, monotonically. So it's a series of steps that may involve actually an intermediate that's going to be more ordered. And by that, I mean that the L12 precursor that's going to form in the middle, that's going to be the first precursor for the crystallization process, is going to have both types of order, structural order, close packed, but also chemical order, so L12, so the distribution of the atoms according to their chemical nature is going to be specified there, and is going to help the promotion process, the crystallization process. And finally, on the right-hand side, we have the final product that's going to be the solid solution, which is going to only include structural order, so this closed pack order, but the result, as we've seen on the previous slide, is going to be chemically disordered, and there will just be remnants of the ordered precursor that are going to be on the outside of the nucleus. So again, we have a mechanism that makes this very ordered phase an intermediate and a promoter of the crystallization process. So they do form in the supercooled liquid, and they are going to serve as a way to trigger the onset of crystal nucleation. And they do continue to form on the surface of the nucleus throughout the crystallization. And again, this novel pathway suggests new ways to understand control and control the formation of solid solutions. And again, these solid solutions, they are key to well, quite a few applications nowadays, as for instance, water splitting, hydrogen production, and the formation of ion tripiolytes. All right, so I'd like to thank you for your attention, thank the group for the work, and thank NSF for funding this work. Thank you again for your attention today.